Welcome to the Explainer. Have you ever wished you had a crystal ball? Some way to know for sure that the decision you're making right now is going to lead to the best possible outcome? Well, in this Explainer, we are going to dive into a seriously powerful framework for making smart choices, even when the future is totally random.
Really think about it. Whether you're trying to figure out an investment, planning a big business strategy, or heck, even just playing a board game, you're constantly making a series of choices where the results are not guaranteed. This Explainer is all about a mathematical framework that was built for that exact problem.
So let's make this real. Imagine you're in charge of a central bank. Your economy can be in one of, let's say, 3 states. You've got high inflation, things are stable, or you're in deflation. You have actions you can take, right? Like raising or lowering interest rates. But here's the kicker. Your actions don't guarantee an outcome. This diagram shows that if you're in that inflation state, your action might move you to stable, or it might not. You're working with probabilities, not certainties.
This kind of puzzle, making a whole series of choices over time to get the best possible result, it actually has a formal name. It's called a sequential optimization problem. And lucky for us, it's not some unsolvable mystery. There's actually a map we can use to navigate it.
And that map? It's called the Markov Decision Process, or MDP for short. This is really the core idea we're going to unpack today. It gives us a super precise way to talk about these kinds of problems, whether you're managing an economy or, teaching a robot how to walk.
At its heart, an MDP is just a model. It's a formal way to think about the whole decision-making process by breaking it down into 4 essential pieces. Once we get these 4 parts, we can start to see exactly how to solve the puzzle. Okay, first up, states. This is simple. States are just all the possible situations or conditions you could find yourself in. In our economy example, the states were inflation, stable, and deflation. It's just a complete list of every possible scenario. Next up, for every one of those states, there's a set of actions you can take. So, if the economy is in that inflation state, your available actions might be to raise interest rates, lower them, or maybe just do nothing at all. These are the levers you actually get to pull.
And here's where the randomness kicks in, the transitions. These define the probability of moving from where you are now to some other state, given the action you just took. So if you're in inflation and you raise rates, there might be, say, a 50% chance you move to stable, a 40% chance you just stay in inflation, and a 10% chance of something else entirely. This is the part that captures all that real-world uncertainty.
And finally, the 4th piece of our map, rewards. This is the feedback loop, and it's absolutely crucial. For every action you take in any given state, you get an immediate score. It could be a positive reward or a negative penalty. A stable economy might give you a big positive reward, while high inflation gives you a nasty negative one. And this is what we're ultimately trying to maximize. Okay, so we've laid out our map, right? We have states, actions, transitions, and rewards. Now for the most important question. What are we actually trying to do with all this? What's the goal?
The goal is to find what's called an optimal policy. Now, you can just think of a policy as a rule book or a complete strategy guide. For every single state on that map, it tells you exactly which action to take. The optimal policy, then, is the rule book that guarantees you'll get the highest possible total reward over the long haul. It's the perfect cheat sheet.
And that's the million-dollar question, isn't it? It's pretty easy to see the immediate reward you get for an action, but some states are really valuable not for what they give you right now, but because they open up a path to huge rewards way down the line. So how do we possibly calculate that long-term potential, that value?
Well, the answer lies in this incredibly elegant and powerful idea called the Bellman equation. It gives us a way to define the value of a state by looking at its neighbors. It basically boils down to this. The value of where you are is just 2 things added together. First, the immediate rewards you get right now, plus the discounted value of all the places you might end up next. And that discount part is just a fancy way of saying a reward today is worth more than a reward tomorrow. It keeps the system focused. The real magic of the Bellman equation is that it creates this beautiful web where the value of every state is linked to the value of every other state. It's the engine that connects the present to all possible futures. And by solving this whole system of equations, we can figure out the true long-term value of every single spot on our map. That value is the key to finding the perfect strategy. So we have our map, and we have the equation that defines our destination. The last piece of the puzzle is, how do we actually solve it? How do we find those values? Well, it turns out there are 2 classic algorithms that can get the job done.
The two main approaches are called policy iteration and value iteration. Now, they both get you to the exact same optimal solution in the end, but they take very different routes to get there. You can think of policy iteration as focusing on making the rulebook better and better, while value iteration is all about figuring out how much each square on the map is worth first.
So, policy iteration is kind of like a two-step dance. First, you take whatever your current policy is, your rulebook, and you evaluate it. You figure out, okay, if I follow these rules, what's the long-term value of every state? Then comes step 2, improvement. You go through your rulebook, and for each state, you greedily pick the action that looks best based on those new values you just calculated. And you just repeat that dance, evaluate, improve, until your policy is perfect and it just stops changing.
Value iteration, on the other hand, takes a more direct route. It doesn't even bother with a rulebook at first. It just uses that Bellman equation over and over again to update its best guess for the true value of every single state. It just keeps sweeping through, refining the values on the map with each pass until they stop changing. And only then, at the very end, once it has that perfect value map, it pulls the optimal policy out in one final easy step.
And this table just lays out the trade-offs perfectly. Look, value iteration often takes more rounds, more iterations to finish. But each one of those rounds is computationally pretty cheap. Policy iteration, however, usually finishes in way fewer steps, but each one of those steps is much more expensive because of that whole evaluation phase. So there's no single best answer here. The right tool really depends on the problem you're trying to solve.
Okay. So this is a really cool framework. But is this just, for academics, does this stuff actually show up anywhere in the real world?
The answer is, oh yeah, it's everywhere. MDPs are the engine running behind a huge amount of modern tech. We're talking about teaching robots how to walk, optimizing incredibly complex global supply chains, creating AI that can play games better than any human, and building financial models to guide investment strategies. Even the speech recognition on your phone uses these same core ideas.
So what's the big takeaway from all this? The Markov Decision Process. It's a universal language. It's a structured way to model and then actually solve some of the most difficult problems we face. Basically, anytime you need to make a sequence of smart decisions in a world you can't totally predict, this is your tool.
And that leaves us with one final thought. Now that you have this framework, this idea of states, actions, transitions, and rewards, what puzzles in your own life or in your work could be mapped out like this? What complex, uncertain decisions could you start to understand and maybe even optimize using this incredible map?